Okay, it is my pleasure to introduce the third speaker of this session, Abdul Zalloum, talking about regularity of Morse geodesics and growth of stable subgroups.
All right, so thanks to the organizers and thanks for introducing me. Okay, so this is based on two joint projects. One is with Ake and one is with Cordis, Russell, and Spriano. Okay, so let's start. Suppose you have a directed labeled graph, gamma, and let O be some unique distinguished vertex of gamma. So you just fix a vertex there once and for all. The collection of words which can be read as labels of directed paths starting at O is called the accepted language of gamma. So you have a directed labeled graph with a unique distinguished vertex, and then any word that you can read as labels starting at O and landing somewhere is called the accepted language of gamma. So for example, if you take this graph, you have your O, and you ask yourself, so what's the accepted language of this graph? The accepted language of, okay, so what's the accepted language of this graph? Well, you can do as many A's as you want. You can do any power of A, but you can also do any power of A followed by any power of B. So the accepted language of this graph is something of this form. It's A to the M, B to the N, where M and N vary in the natural numbers. Okay, so suppose you have a finite set A, and let L be an infinite subset of the free monoid on A. I want it to be infinite because the results are only interesting when L is infinite. So I'm fixing an infinite subset of A star. And this infinite subset is said to be a regular language if it coincides, if it happens to be the accepted language of some finite directed labeled graph. So for example, if you have this language and you ask yourself, is it a regular language? Well, asking if this is a regular language is equivalent to asking, can you come up with a finite directed labeled graph that reads precisely this? And of course you can, because we just did this example. So the answer here is yes. Now, if you take the following other language, which looks very similar, it's A to the N, B to the N, where the N's match, and you ask yourself, is this a regular language? You can sit down and try to come up with a finite directed labeled graph that reads precisely this, but you won't be able to because it's not regular. So the question that poses itself is, what's so different between these two languages that made the first regular and the second not? Okay, so we have these two languages which look very similar. The only difference is that in the first language, the N and the M's did not match, but in the second language, they had to match. And the first one is regular and the second one is not. So why is that? And why is that? We'll tell you how to think of regular languages. So in the first example, the rules of being in the language say, do any power of A's and follow them by any powers of B's. You don't need to remember how many A's you've done to do the B's. You could do 1,000,000 A's and follow them by 2 B's. So the number of A's you've done to start with is irrelevant. You don't need to have any memory of what you have done. While in the second one, if you've done 100 A's, you have to remember that you've done 100 A's to do 100 B's, etc. So one of the ways to think of a regular language is it's something that has finite memory, right? It's something that only has a finite amount of memory. So this is the first piece of intuition. You have an infinite set, which is produced by a finite graph, which means that your infinite set is not really infinite, right? It's infinite, but in a very finite way. It only contains a finite number of patterns that you repeat over and over to get your infinite set. Another piece of intuition of what a regular language is the following. So being a regular language means if I hand you a super long word W, and you know that this W lives in your language, and then you append one letter to W. So you add WA and you ask yourself, is WA again in L or not? The question of whether WA is again in L or not is determined by only finitely many rules. And most frequently, these rules are just the last few letters we have just done. In other words, if you have a super long word W that you know is in L and you ask whether WA is in L or not, this question is determined by only the last few steps. You don't need to keep track of the entire W to tell whether WA is an L or not. This is not 100% precise, by the way, but it should give you an idea of what a regular language is. That's the idea. The idea is you only need a finite amount of data to decide if WA is an L or not. Quickly, I want to show you that this is actually related to geometry. Why is it related to geometry? So let's look at T3. And let's try to understand geodesics in this tree. So I have this tree, and I ask myself, how do geodesics look like? So suppose you have the following geodesic that you know is a geodesic so far, right? So far I'm a geodesic. And let's say that at this point, I fail to be a geodesic, okay? Why? How can you fail being a geodesic in this particular example? Well, you fail being a geodesic by backtracking. In other words, you fail being a geodesic locally. If your length is a billion zillion and you are a geodesic so far, if the new step that you add again is a geodesic, then you're a geodesic, right? In other words, you don't need to keep track of the entire history of your geodesic to tell whether you're a geodesic or not. If you happen to be a geodesic locally, you are a geodesic globally. However, the situation in an infinite wedge of circles is quite different, right? If you have an infinite wedge of circles and you're testing if you're a geodesic or not, and you look, for example, you're a geodesic, you're a geodesic, you're a geodesic, you're a geodesic, you're a geodesic. But after you pass this point, you're not a geodesic, and you're not a geodesic not because you failed it locally, because here you are still a geodesic, and here you are still a geodesic. You needed to keep track of the entire thing to decide whether you're a geodesic or not, okay? And you can also, this is an infinite wedge of circles, right? So we actually do have larger and larger circles, and the amount of data you need to keep track of, so if you have a larger circle, the amount of data you need to keep track of to decide if you're a geodesic or not is now larger. You now need to keep track of this entire thing, right? So the point is, you can't tell being a geodesic by only looking at finite pieces. Okay, so it turns out that, so first off, notice that this is the idea here, being a geodesic locally is the same as the regular language idea, right? Being a regular language meant you really only needed to take the last few steps to decide whether you're in the language or not. So something like this should be a regular language and something like this should not be a regular language, okay? And this is actually precise. So this is a classic theorem by Cannon. So he showed the following: if you give me any finitely generated hyperbolic group, then regardless of what your generating set is, if you look at the Cayley graph and you look at all geodesics, then that does form a regular language, precisely for the same type of idea that we just saw. Negative curvature is, it has some local to global features to it that tells you that you really only need to check things locally to decide whether you're a geodesic or not. Okay, so let me quickly define what the growth of a group is. Suppose you have a group. The growth of the group is at the value n, you just count the number of group elements of length at most n. Okay, and the growth is said to be rational if an satisfies a finite linear recursion. What do I mean by satisfying a finite linear recursion? So being a rational growth is equivalent to saying that the growth function an looks something like maybe 3an minus 1 plus 5an minus 2. Okay, that's what it means to have rational growth. And this now, up just to put it more precisely. So an having rational growth means an to tell the nth term, you need only to know the last uniformly k terms. That's what it means to have a rational growth. And again, I want to point out that this idea is very similar to the idea of a regular language, right? Having a finite linear recursion just means in order to tell the nth term, all you need to know is the last k terms. You don't need to know every step of the sequence to tell the nth step. You can spit out the nth step by only knowing the last 5 steps. Okay, so it's not very surprising then if I tell you that whenever you have a group that has a regular language of geodesics, then the growth of that group is rational. Because again, recall rational just meant that you satisfy a finite linear recursion. Okay, so this tells us that hyperbolic groups have rational growth because we just saw that hyperbolic groups have a regular language for their geodesics. Okay, and here's just a quick combinatorial fact. To say that a sequence an satisfies a finite linear recursion is equivalent to saying that once you look at the generating function of this sequence, if I look at the generating function corresponding to the sequence, what you get is a rational function. So this is p of x over q of x. So that's why we call it such a growth rational, because satisfying a finite linear recursion is equivalent to having your generating function look like p of x over q of x. Okay, so suppose you have a geodesic metric space. We're going to make a definition. A geodesic is said to be decontracting if whenever you take a ball disjoint from your geodesic and you project it, you do the nearest point projection to your geodesic, you get a subset of diameter at most t. Okay, so something, regardless of whether your ball is small or large, as long as your ball is disjoint from your geodesic and you project, you get something of a unit of diameter d. Okay, so if you're thinking of something like R2, then there aren't any such infinite geodesics. In other words, if you give me an infinite line in R2, well, clearly, if you take the ball larger and larger, you will get larger and larger projections. So the diameter of the projection is not bounded. However, if you look at something like F2, and you take an infinite line, and you take any ball which is disjoint, so here is a disjoint ball, and you project it, you're going to get a subset of diameter 0. Okay, so every geodesic in F2 is 0 contracting, while no infinite geodesic in R2 is. In fact, so we saw an example where you don't have any contracting geodesics. We saw an example where every geodesic is contracting. There are examples where some geodesics are contracting and some are not. Okay, but the property that every geodesic is decontracting for the same d characterizes being a hyperbolic space. In other words, a space is said to be hyperbolic if and only if there exists a d where every geodesic in the space is decontracting. So from this perspective, you can think of decontracting geodesics as generalizing hyperbolicity, right? Because they exist in other places. They don't only exist in hyperbolic spaces, and they characterize being a grown-up hyperbolic space. So earlier we saw that if you give me a hyperbolic group, a theorem due to Cannon told us that the language of all geodesics is a regular language. So a natural question to ask is, suppose you give me some finitely generated group, and you look at the collection of decontracting geodesics. I'm not looking at all geodesics anymore. I'm only going to look at the decontracting ones. Does this form a regular language or not? And the answer to this question is yes. In other words, if you give me any finitely generated group, then the language of decontracting geodesics in that group is a regular language. So this clearly recovers Cannon theorems, and it shows that being a regular language is a proper, it's really a property about contraction more, well, anyway, yeah. So an interesting consequence to this is that you never see infinite contracting geodesics in torsion groups. If I hand you a group which is torsion, then it cannot contain an infinite contracting geodesic. And the reason for this is some, if you have an infinite contracting geodesic in a torsion group, then you take your infinite contracting geodesic and you run it by your finite labeled graph. And at some point you have to go through a loop, right? And then if you repeat this loop over and over and over, then what you're having is an infinite order isometry. So any torsion group cannot contain an infinite contracting geodesic. Another interesting consequence of this theorem here is that if you give me a group which contains an infinite contracting geodesic, then this group must be acylindrically hyperbolic. So there's a theorem due to Sisto, Osen, and Bestvina that shows you that if you have a contracting element in a group, then you must be acylindrically hyperbolic. Okay, but this theorem here, it improves it. It says, well, you don't really have to have a contracting element. All you really need to have is an infinite contracting geodesic, because that gives you a contracting element. Okay. Okay, good. So let's move on. So a geodesic is said to be M Morse if quasi-geodesics. So here is a geodesic. It's said to be M Morse if every KC quasi-geodesic remains close to your geodesic. So if you give me a KC quasi-geodesic, you're going to remain close. And how close depends on the KC. Of course, it will depend on the KC. If you take K and C being bad, then the M that you will get will be worse. So right. So that's what it means to be M Morse. Every KC quasi-geodesic remains M close to your line. And it's again true that being M Morse characterizes hyperbolic spaces. In other words, a group is hyperbolic if and only if there exists a single M where every geodesic in the group is M Morse. So it's natural to ask, well, okay, so actually let me just quickly say, what's the advantage of Morse geodesics over contracting geodesics? Morse geodesics appear in lots of in more spaces. So you see them in the mapping class groups, you see them in AuTF, and You see them in hierarchical hyperbolic spaces. You see them in cat-zero cube complexes. Contracting geodesics, you do see them, for example, in cat-zero spaces, but we don't know if you see any of them in mapping class groups. The other reason why the Morse notion is interesting is because it describes lots of interesting subgroups of lots of interesting groups. For example, it describes convex compact subgroups of mapping class groups, and it also describes lexicodromic subgroups of right-angled arcing groups. So, right, so this is a reason to care about M-Morse geodesics. Okay, so you have a finitely generated group and you fix a gauge M, and you ask yourself, is the language of M-Morse geodesics a regular language? And the answer to this is no, because Fink gave an example of a torsion group which contains an infinite Morse geodesic. Okay, having a torsion group containing an infinite Morse geodesic immediately implies that you cannot possibly have a regular language for M-Morse geodesics, because that will immediately imply a Morse element. Now, this is counterintuitive to the claim that Morse geodesics are hyperbolic-like. How can you, on one hand, claim to be hyperbolic-like? On the other hand, you see them in torsion groups. I mean, torsion groups shouldn't have anything to do with hyperbolicity, right? But so it's a bit weird. And it causes this problem and a few other problems. Okay, so we have these three guys, Russell, Cipriano, and Tran, and they said, well, this is problematic, and we either sit down here and cry or we do something meaningful. But they did something meaningful. So here is what they did. They introduced a category of spaces called Morse local to global spaces. And what this is, so what does it mean to be a Morse local to global space? It means that you're a geodesic metric space where if you happen to be locally Morse, then you are globally Morse. This needs, I need to quantify it more formally, but this is the idea. The idea is that if I hand you an infinite geodesic, all right, and you want to tell if it's Morse or not, there exists a large enough window, there is a large enough L, such that if you happen to be Morse in this large enough L everywhere, then the entire geodesic line is Morse. Okay, that's the idea. Okay, so just very quickly, lots of the interesting examples do satisfy the Morse local to global property. So for example, mapping class groups satisfy the Morse local to global property. Cat-zero groups satisfy the Morse local to global property. Fundamental groups of closed tree manifolds satisfy the Morse local to global property. Hierarchical hyperbolic groups satisfy it. So in a sense, I don't want to say the interesting groups because yeah, I mean, most interesting groups, and I know this is not a fair statement, but in some sense, most interesting groups do satisfy the Morse local to global property. And one of the very interesting questions, in my opinion, is that does out of n satisfy the Morse local to global property? Okay, anyway, so we have a property. Why is it useful? Lots of things turn out to be true for Morse local to global spaces, which are not true in general. For example, we saw that the language of geodesic, the language of M-Morse geodesics in general is not a regular language. So you can ask, is it a regular language in the category of Morse local to global spaces? And the answer is yes. If you give me a Morse local to global space and you look at the collection of M-Morse geodesics, then that does form a regular language, all right? Okay, so let me give you a definition very quickly. A subgroup is said to be stable. So a subgroup is said to be stable if any 2 points are connected by a uniformly M-Morse geodesic, which stays uniformly close to the group, okay? So a subgroup being stable means any 2 points can be connected by some M-Morse geodesic that stays K close to the group. And the M is uniform, the K is uniform. It's uniform over all pairs of points in your group. That's what it means to be M-Morse. That's what it means to be stable. And if you are a hyperbolic group, then being stable is equivalent to just being quasi-convex. If you are, let's say you're in a right-angled arcing group, then being stable is equivalent to being purely lexicodromic. And some people need to be cited for that. Menga has Taylor and somewhere else who hopefully won't be mad at me. Anyway, so 3 people. Yeah, sure. Anyway, so that's the idea. Okay, great. Okay, so we saw that there is some relationship between having rational growth and regular languages. And so this theorem makes it precise. So suppose you have a Morse local to global group. if you have a stable subgroup in this group, then the growth of H in G is rational. What I mean is, if you take larger and larger balls in the K graph and you only count elements in H, then that's a rational function. Okay. And another interesting consequence of this is that if you give me a stable subgroup of a Morse local to global group, then the growth rates of this stable subgroup is strictly smaller than the growth rate of the entire group. And I should say that, so this theorem here, it was known by Dahmani, Footer, and Wise in the context of hyperbolic groups. And this theorem it extends their theorem from the setting of hyperbolic groups, the setting of ket zero groups and mapping class groups and ket zero groups, mapping class groups, fundamental groups of hyperbolically manifolds, etc. Okay, good. What else? So here are two questions that I think are extremely interesting. The first is, does out of n satisfy the, well, maybe I should tell you why you should care about the Morse local to global property first. So hopefully I give you some reasons why having the Morse local to global property is useful. So for example, you do get regular languages for M Morse geodesics. You understand the growth of stable subgroups much better in such groups. But there are lots of other interesting consequences of being Morse local to global that I did not mention. One of them is due to Russell, Cipriano, and Tran, which is for any stable subgroup H in a Morse local to global group G, you can always find the Morse elements, little g, such that this subgroup is H star G. So you can always find a free product. For any stable subgroup, you can always find a free product with your H. And this is extremely useful, right? Like it's the type of thing that you would like to prove about. It's the type of thing that you'd like to prove about stable subgroups. Right. So okay. Right. So yeah, I'll just end with. I'm actually quite surprised that I ended up 3 minutes earlier than I expected to. But anyway, yeah. So two questions that I really like: does out of n satisfy the Morse local to global property, and does SL and Z? Actually, the question for SL and Z is a bit more subtle. I don't really know if SL and Z has any infinite Morse geodesics. And I think that, yeah, I think that would have lots of interest. So can you come up with an infinite M Morse geodesic in SL and Z? And yeah, anyway, so I'll just stop here, and thanks for listening.
Excellent. Let's thank Abdul. Are there any questions?
Hi, Abdul. I have a question. Michael here.
Yeah. Yeah.
So I'm just curious, like very often people show that something is rational, but or not, but when the answer is positive, have you also been concerned, or have you cared about like how big the finite state automaton is? Because like, for example, the standard proof that shows that the geodesics in hyperbolic groups are rational is actually a bit of a cheating, because the size of the automaton is doubly exponential, which is not small. Doubly exponential in delta.
Is it exponential? You said in delta? I know, yeah.
Doubly. So
okay.
It's
I see. Yeah. So if that's the case, then it's definitely the case in ours, because the proof is very similar to Cannon's proof. It's a cone types argument. Okay. So I'm pretty like our theorem recovers, like our proof recovers his. So like in the yeah. So in the sense that if they have the exponential growth, we certainly also have exponential. If the number is exponential in terms of the So wait a second. So
yep, that's a good answer. Thank you.
Okay. I mean, I don't see myself. Do you see me or not?
No, your camera.
No, I cannot see you.
Okay, sorry. My video was on at the start. Did it just turn off at some point?
No, we didn't. I have not been able to see you the whole time.
You haven't seen me throughout the whole thing. How sad.